leading edge vortices. The unstable leading edge vortex is like a dynamic stall phenomenon. And this is an NES simulation of the dynamic stall phenomenon. What's the dynamic stall phenomenon? So we have a rapid variation of the angle of attack. So maybe from 0 to 20 degrees, but rapid. We're not doing it slowly, because slowly you will have the steady response. We're doing it rapidly. So let's see here. Let's get it from the beginning. And let me change this to pointer. So this is a slow motion video for the flow field and the airfoil motion. So the airfoil motion should be much more rapid than this. But anyway, what happens? Actually, you can see it clearly in this picture, the down three-dimensional. The separation point, I mean, if you increase the angle of attack, the separation point moves forward. You will see here the separation point moves forward, and from there as well. I can go back a little bit to see this. Okay. So just look at here and also over there how the separation point moves forward. So anyway, as the separation point moves forward, you operate at larger angle of attack. As the separation point moves forward until it reaches to the leading edge, then there will be separation at the leading edge. The separation at the leading edge will be accompanied by a leading edge vortex. The leading edge vortex will grow in strength and moves downstream as time evolves. One thing that I want you to notice here, aside from this whole video, look at this. This blue curve is the time evolution of the angle of attack. As you increase your angle of attack, the left here, the black is the angle of attack, the blue is the left. As you increase your angle of attack, the left increases. Now the angle of attack is stationary, so you increase from 0 to say 20 degrees or something, and you just keep there. So that you expect the left increases as you increase the angle of attack, and then stays as this, right? This is the steady behavior, but this is here an unsteady behavior. So up to this point, the left should separate, right? It actually keeps increasing as you see here. And this is due to the leading edge vortex. This behavior is due to the leading edge vortex. The issue is that the leading edge vortex forms and grows and generates more lift, but doesn't stay there. There's no reason to stay there. It's a vortex. It's not a circulatory flow like the bound circulation. It's a vortex in the flow, so it will move with the flow. So it convects downstream. As it convects downstream, actually, you have here something like, let's get this bend. So you have your bound circulation, and now you have a vortex moving. This guy moves downstream, gamma leading edge vortex. So you have left due to that guy and left due to that guy. So the center of pressure is supposed to be at the coda chord. Now it moves, right? So this is the resultant lift force due to both. It moves, its location moves as this vortex moves. So what you get out of that, you get a nose down moment, okay? Huge nose down moment. The point this leading edge vortex leaves the trailing edge, you have almost complete flow separation. You can see it from the video. Okay, so this is the leading edge vortex is forming, growing, and moving downstream. Here it's growing and then it will move downstream. And you can notice the nice interaction between the trailing edge vortex and the leading edge vortex. So anyway, as you can see here, we did not reach, this is highly unsteady flow. The lift didn't reach a steady value, and it significantly overshoots. Okay? The issue is that the leading edge vortex is not stationary, it doesn't stay, and it convects, and this leads to a huge lift drop. This is the situation for the dynamic stroke phenomenon, and this leading edge vortex is not stable. Insects cannot operate like this because you get a little bit of lift more, but then it's not sustained. On the other hand, there is a stable leading edge vortex, like on highly swept and delta wings. So let's look at this. I have the pen here. So if you have a wing highly swept, and this is the flow, you have a span-wise flow, right? It's like cosine. And if it's highly swept, this span-wise flow is much stronger, right? So when a leading edge vortex is forming here, this span-wise flow takes it with it to the trailing edge, to the tips of the wing. And you have a picture like this. Remember, you can always stabilize a vortex. Stabilize means keeping it attached if you have a radial flow in its core. So, you have a swirl around a radial flow. This is a stable thing. It will not just, turbulence will not affect it much, by the way. So, because of this strong radial flow, you can stabilize a vortex around, this is one of the famous examples, you can stabilize a vortex around the radial flow. So what's the source of this radial flow here? It's because of the span-wise flow, because of this high sweep kind of thing. So leading edge vortices were observed way before insect day. This span-wise flow also exists in helicopter and propeller blades. So people also know that helicopters and propeller blades, we do have stabilized leading edge vortices at large angles of attack. Why? What is the source of the span-wise flow here? So we said, okay, to stabilize the leading edge vortex, you need a span-wise flow. So what's this over here? The source of the span-wise flow, because you have an inclined edge, so you get a span-wise flow. What's the source of the span-wise flow for a helicopter blade? Any idea, any suggestion? Similar, but not exactly the same. I mean, yes, you can say yes for centrifugal force when you apply it to the fluid mechanics equation. So the thing is, it's the momentum at the end of the day. The thing is, when a blade rotates like this, so every section has a velocity omega r. So the outer sections are much, right? They are faster than the inboard sections, and if this is faster, it has lower pressure in steady thing, and it has lower pressure. The flow will go from the high pressure to the lower pressure. So you have a span-wise flow for helicopter blades and propeller blades, which is, you can guess, it's the same reason for flapping flight. Also flapping flight, we have this kind of rotary motion that stabilizes the leading edge vortex. Okay, so this is, in a nutshell, the story of what is a leading edge vortex and where do we see it. Turns out that it plays the major role for flapping flight. Okay, let's see, let's talk about Polhamos's leading edge. Yes, keep please. Leading edge suction analogy. So this is by Polhamos. It's a famous NASA report 1966 about the leading edge, because at that time the community was very interested in determining the extra lift due to a leading edge vortex. How much lift, how much more lift do we get? So we need an analytical expression for that. So let's see. So it's not, it's not very physical, but it has, it has ingenuity behind it. So let's see. So we have this kind of flat plate. We have our, the normal force. So this is our lift coefficient, which is 2 pi. I'll do it like this. This is 2 pi sine alpha, okay? And 2 pi is for a flat plate. If it's a 3-dimensional wing, it's no longer 2 pi. The CL alpha 3-dimensional is what? Is 2 pi divided by at least 1 plus 2 over aspect ratio, right? This is the Prandtl lifting line theory, the simplest correction that you can have. So the 2 pi 3-dimensional, because of the aspect ratio, you get CL alpha, which is less than 2 pi, right? So for infinite aspect ratio, you get 2 pi, but this guy is anything less than infinity. So this is this decreases, the whole denominator increases, and the CL alpha decreases. Okay. So this guy decreases, this guy decreases. So we don't have 2 pi anymore. Actually, we have something like CL alpha sine alpha, or